Many people think that astronomers want telescopes with big magnifications, but this is actually not the case. What astronomers want is as much information as possible. They're trying to collect as much light as they can. Each photon is a piece of information. That's information that we didn't have before. And that's what astronomers want to do, collect as much light as possible. This allows them to discern many things, but one of them is to see two objects as indeed two separate objects. This is called resolution, and here's an example right here. You can see we have two distinct objects, but with lower resolution, you still tell that they're separate, but they're not visually separate, right? And down here, they truly look to be one object. This is what happens, by the way, when you look up at stars. Most of the stars in the sky are binaries. That is, there are two of them. But when you look, you only see one. And when you use a telescope, if it's sufficiently powerful enough, you'll be able to see, oh, that star that I thought was only one is actually two. And that's the case. With increased resolution, with more information, we can discern that these are indeed two separate objects. And the formula for this theta min equals 1.22 times the wavelength divided by the width of the optic. This is the minimum angle that can be resolved. This is the wavelength of the light, and this, as I already mentioned, is the width of the optic. Okay. Now, let's say that I've got an optic, a mirror, that is extremely curved. This is very curved. You don't actually see optics like this being used in telescopes, but we'll pretend we've got one like this, and we'll see why they're not used. So when I say the diameter, or I should say the width, that's just the diameter here. This is the diameter, which is also the width of the optic. And by the way, I keep saying diameter because a lot of these telescopes, a lot of the mirrors in them are circular. But really it is the width that we care about. Anyway, you can imagine I have a different telescope that has the same width, but is flatter, that is not as curved. And there are many advantages to this one over this one. And they're practical advantages. You can see this ultimately is a longer line. So that means more material is needed to build this mirror. Less is needed to build this one. Additionally, this is going to weigh more. It's going to be harder to support. This is going to be easier to support because it's lighter. Now, we learned that for mirrors, the focal length is half of the radius of curvature. The radius of curvature for this one might be right here, because the smaller, for objects that are highly curved, they have a smaller radius of curvature. Objects that are flatter have a much larger radius of curvature. The radius of curvature for this one is, probably beyond, it's bigger than what I can draw here on this whiteboard. So this has a large radius of curvature. This one has a much smaller one. So this would have a small focal length. This one would have a big focal length. And why does that matter? Because the magnification formula for a telescope is the negative of the focal length of the objective divided by the focal length of the eyepiece. The bigger the focal length of the objective, the more magnified the image is going to be. So you want something that has a large width. You want an optic, a mirror generally, that has a large width. But for practical reasons, you still need it curved, but you do want it flatter. And by making it flatter, you're going to increase the radius of curvature, which is going to increase the focal length. And because you've increased the focal length, as a byproduct, you increase the magnification. But that's just a happy byproduct. That's not the goal. The goal is to collect as much light, to collect as much information as possible. And that's why we want a large width and consequently large mirrors in our telescopes, so that we can see objects that are two distinct objects as indeed two distinct objects.